I want to begin with a remarkable idea. It started out as a thought experiment of Isaac Newton. It's based on a famous diagram in the Principia. I doubt that Newton ever dreamed it would become a reality. The idea, I mean, is the artificial Earth satellite. Now, here's Newton's version. Imagine a cannon up on a high mountain on a spherical Earth. The cannon is fired, and the cannonball shoots out horizontally. If we ignore all air resistance and consider only gravity, how does the cannonball move? If the ball is fired with one speed, it follows a curved arc and hits the ground. Fired somewhat faster, the ball goes further. Galileo said that the shape of the path is a parabola, but he knew that this was only approximate, that this was neglecting the curvature of the Earth. So Newton says, let's take the curvature of the Earth into account. A very fast cannonball goes part way around the Earth. A very, very fast cannonball goes halfway around the Earth. And if the cannonball is fired a little faster, the cannonball does not actually hit the ground at all. It follows a circular path around the planet. Gravity does curve the trajectory of the cannonball, but only enough to make it go around in a circle. The cannonball orbits the Earth, an artificial moon. This is how Newton explains his ideas about orbital motion. Of course, he isn't really thinking about cannonballs. He's thinking about the orbits of planets and moons. So in this lecture, we will once again follow his lead, Newton's lead, and see how the concepts of mechanics, including energy and angular momentum, apply to orbital motion, or anything moving around the sun or the Earth, anywhere in the universe. So, back in lecture 3, Johannes Kepler described the motions of the planets around the sun. 3 laws of planetary motion. The law of ellipses, the orbit of a planet is an ellipse with the sun at one focus. The law of equal areas, a line between the sun and a planet sweeps out equal areas in equal times. And the harmonic law, the cube of the semi-major axis of a planet's orbit is proportional to the square of its orbital period. We later saw that Newton explained Kepler's laws. They followed from his own laws of motion and his law of universal gravitation. That is, let big M represent the sun's mass and little m be the planet's mass, and r is the distance between the sun and the planet. Then Newton says the sun pulls on the planet with a force F equal to g times big M times little m over r squared. The force is proportional to 1 divided by r squared, an exponent of 2 in the denominator. That means that twice as far away yields a force of gravity that is only 1/4 as strong. We could imagine a universe in which this exponent was different. Not 2, it might be maybe 1 or 3 or 2.416. And Newton says a different law of force would result in different kinds of orbits. For most laws of force that we could imagine, the orbits would not even be closed curves in space. They would be complicated spiral patterns. The elliptical orbits that we see in nature are a kind of signature of the law of gravity. The same laws that govern the motion of any orbiting body, be it a planet or a satellite or a moon. So let's return to Newton's cannonball satellite. If we fire it fast enough, it moves in a circular path and it never falls to the ground. So how fast is fast enough? And Newton is able to figure out the answer. The orbital speed of a circular orbit of radius r around a body of mass m, a planet or the sun or something, a circular orbit, the circular orbit velocity, v circ we'll call it, equals the square root of g times m divided by r. Now, there are lots of things to notice here. First of all, the circular orbit speed does not depend on the mass, we might call it little m, of the satellite. And that makes sense. It's yet another expression of the principle of equivalence. Any object would move the same way under the force of gravity. The circular orbit speed does depend on the mass of the body that you're orbiting. A more massive planet with a stronger gravity requires a faster orbit. And the circular orbit speed depends on the distance. A wider orbit only requires a slower speed for a circular orbit. In fact, the equation looks rather familiar. It's almost identical to the formula that we derived in Lecture 6 for escape speed. The exact relationship between the two is quite simple. At a given distance, the escape speed is just the square root of 2 times the circular orbit speed. Putting it a different way, roughly speaking, the circular orbit speed is about 70% of the escape speed. Now you can use our equation for circular orbit speed to calculate some interesting things. So for example, the Earth follows a nearly circular orbit around the Sun. The Sun's mass is about 2 times 10 to the 30th power kilograms, and the Earth's orbit has a radius of 1 astronomical unit, which is 150 million kilometers, which is 1.5 times 10 to the 11th power meters. So, remembering the value of g, we can calculate and find that the Earth's orbital speed, v circular, is 29,800 meters per second, about 30 kilometers per second. And that's pretty fast. That's 100 times faster than a jetliner. Now, there's a common misconception about orbits. They're not like train tracks. An orbit is just a mathematical path through space. Nothing bad necessarily happens if you get off your orbit. If your velocity changes a little, then your orbital path also changes, maybe just a little. So for example, consider a spaceship at a distance r from the center of the Earth. It's initially moving horizontally, that is to say, at right angles to a line from the spaceship to the Earth, and it's moving at a speed v. If v equals v circ, then the spaceship follows a circular orbit of that radius. But if v is less than v circ, what happens? Does the spaceship spiral inward out of control? Not at all. The spaceship just follows an elliptical orbit, one that lies inside the circular path. The Earth's center is at one focus, that is to say, the orbit still follows Kepler's first law. And the initial point in the orbit is the point furthest from the Earth on the orbit. It's called the apogee of the orbit. And on the other side of the orbit is the point closest to the Earth, called the perigee. Now, an even slower initial velocity will make the perigee that much closer to the Earth. And if the initial speed is too low, of course, then the orbit will intersect the surface of the Earth. The spaceship crashes. What if the initial speed v is greater than the circular orbit speed? Then the spaceship also follows an elliptical orbit, but this ellipse is larger. It's outside of the circular path. The starting point is now the perigee of the orbit. And if the speed is large enough, larger than the escape speed, the orbit is not a closed ellipse at all. The spaceship follows a curving path out into space. Now, we've been talking about a spaceship orbiting the Earth, but everything is exactly the same for something orbiting the Sun, except the near and far points on the orbit are called perihelion and aphelion. And for general orbits, we might call those near and far points the pericenter and apocenter of the orbit. So to describe an orbit precisely, we need to specify a couple of key measurements for the orbit. First, as we've already said, the major axis is the total length of the ellipse. And it isn't hard to see that this major axis equals the pericenter distance plus the apocenter distance. So the semi-major axis is just 1/2 times the major axis, and for a circular orbit, that semi-major axis is just the radius of the circle of the orbit. And every point is a pericenter, and every point is an apocenter. The second key measurement is called E, the eccentricity of the ellipse. Now, eccentricity is the degree of flattening. E equal to 0 means that the ellipse is actually a circle. An E near to 1 means that it's a very long, thin ellipse. And planetary orbits are usually pretty circular. For example, the Earth's orbit has an E equal to 0.017, an almost perfect circle. Mercury's orbit has E equal to 0.21. It's significantly elliptical. It's not really very close to a circle. Any comets move through the solar system with elliptical orbits with E close to 1. For example, Comet Halley has about E equal to 0.97. Its perihelion is about 0.6 astronomical units within the Earth's orbit. It's closer to the Sun, in fact, than the planet Venus. Its aphelion is about 35 astronomical units out beyond the orbit of Neptune. Now, as an aside, this particular comet is named after Edmund Halley, who's a friend of Newton's. Halley used Newton's laws to work out the orbit of the Great Comet of 1682, and he predicted that it would return 76 years later in 1758. Now, Halley died long before that date, but when the comet did reappear, right on schedule, it was named in his honor. Now, in serious orbital mechanics, we'd need to measure the elliptical orbit in other ways. For example, each orbit lies in a plane, but different orbits can be in different planes. For example, the orbit of Mercury is inclined at 7 degrees with respect to the Earth's orbit. So we would need to note the orbital inclination. Also, the line of the major axis might be oriented in any direction in the plane of the orbit. So in all, we need about 6 numbers. They're called orbital elements to exactly specify which orbit we're talking about. But the most important orbital elements are the semi-major axis and the eccentricity. Okay, so what determines the orbital elements of a planet or a satellite? The answer is physics. For instance, the semi-major axis is related to the total mechanical energy of the body, the sum of the kinetic energy and the potential energy. Now, that sum is negative for an elliptical orbit. Kinetic energy is positive, of course, but potential energy is negative. Smaller, closer orbits have lower total energy. The potential energy is more negative for those orbits. Now, if only gravity acts, if only Newton's 1/r² gravitational force is important, then the orbital elements will stay constant. But if some other force acts, thrust from our rocket motors, say, the orbital elements can be changed. For example, consider a satellite in orbit around the Earth. It's in what we call low Earth orbit, only a few hundred kilometers above the ground. The International Space Station, for example, orbits about 400 kilometers above the surface. There are only traces of the atmosphere present at such altitudes. But there is a tiny drag force on the satellite. So the question is, how does this air friction affect the orbit? The answer is an interesting mix of common sense and surprise. First, the effect of friction is to decrease the total energy of the satellite. That is to say, some of the mechanical energy of the satellite is converted into heat. The very thin air up at hundreds of kilometers altitude heats up, and also the satellite heats up a little bit. Thus, the satellite will have to shift to an orbit with a lower mechanical energy, a lower kinetic energy plus potential energy. But as we said, this would be an orbit with a smaller radius. So what happens is the satellite slowly loses altitude. But remember, a lower orbit is a faster orbit. The orbital speed is faster. So the satellite actually winds up moving more rapidly, though in a lower orbit. This seems paradoxical. The effect of friction is actually to speed the satellite up. So quantitatively, it works out like this. Friction reduces the satellite's energy by a small amount, let's say 1,000 joules. 1,000 joules of its mechanical energy is turned into heat by friction. And what happens is that the orbit gets lower. The satellite gets closer to the Earth. So its potential energy gets lower. In fact, the potential energy gets lower by 2,000 joules. So the satellite speeds up. It's accelerated by the gravitational pull of the Earth as it moves downward, and its kinetic energy increases by 1,000 joules. And it all balances out. The potential energy goes down by 2,000 joules, the kinetic energy goes up by 1,000 joules, and 1,000 joules are turned into heat. Energy is conserved. It all does make sense, even though the conclusion sounds odd. If the satellite loses a little energy by frictional heating, in the long run, it goes faster. And the reason for this counterintuitive behavior is the way that gravity shapes the motion of an orbiting satellite. Gravity is responsible. So removing energy from a system shaped by gravity can actually speed things up. At this point in our discussion, that paradox seems merely a curiosity, but I want you to remember it. It's our first glimpse of a significant characteristic of gravity. How significant? Cosmically significant. Literally everything you can see in some measure owes its existence to this gravitational paradox. I'll save that story for later, briefly in Lecture 11, and then more fully at the end of our course in Lecture 23. Let's go back to our spaceship moving near the Earth. Different velocities for the spaceship will lead to different elliptical orbits, but if it's moving fast enough, at the escape speed or better, then it will not just follow a closed ellipse around the Earth. Instead, it will fly off into deep space. So what's the shape of the orbit? What's the shape of the path then? Newton analyzed motion like this. He showed that the paths of escaping bodies were also simple geometrical shapes. So suppose the spaceship is moving at exactly the escape velocity. That means that its kinetic energy plus potential energy, remember, equals 0. So the spaceship has just barely enough energy to get away from the Earth. And in this case, Newton found that the shape of its orbit is a parabola. If the spaceship is moving faster than the escape velocity, its kinetic energy plus potential energy, its total energy, is greater than 0. And then the path through space is a hyperbola. So the possible shapes of the spaceship orbit are circles, ellipses, parabolas, and hyperbolas. You might remember from geometry that these 4 kinds of shapes are the so-called conic sections, the curves you get if you slice a 3-dimensional cone by a plane. That's beautiful geometry. But the point for us is that these possible orbits are all first cousins, mathematically speaking. A circle is a kind of perfectly symmetric ellipse. A parabola is like an ellipse in which one end has been stretched out to an infinite distance, and so on. We can measure eccentricity and other orbital elements for parabolas and hyperbolas, as well as for ellipses. So it's useful to put everything together in a table of the possible types of orbits, along with some of their characteristics. First of all, a circular orbit. A circular orbit is a closed orbit with eccentricity 0. And the circular orbit speed is given by the formula we saw before. Total energy of the orbiting body in a circular orbit is its kinetic energy plus its potential energy is less than 0. It's a negative total energy. Next, consider an elliptical orbit. It's also a closed orbit, but its eccentricity is somewhere between 0 and 1. The speed depends on the details, but that speed must be less than the escape speed. And again, the total energy of the orbiting body, its kinetic plus potential energy, is negative. But now let's consider a parabolic orbit. This is not closed, it's an escape orbit, and the eccentricity is exactly equal to 1. The speed is exactly the escape speed, v sub escape, and the total energy, kinetic energy plus potential energy, is exactly 0. Finally, what about a hyperbolic orbit? This is also not closed. It's an escape orbit with an eccentricity, in this case, greater than 1. The speed in a hyperbolic orbit is greater than the escape speed, and the total energy, kinetic energy plus potential energy, is greater than 0. It's positive. And these are the kinds of orbits that gravity permits around a massive body. So let's now put that knowledge to work. Suppose our spaceship is going around the Earth in a low circular orbit, but we want to be orbiting in a circular orbit that is farther away from the Earth. For example, consider a communication satellite. When it is first launched, it is often placed in a low parking orbit, a few hundred kilometers up. But we want to have it out in a special circular orbit, about 42,000 kilometers in radius. Why? Because an orbit of that radius takes exactly 24 hours to go around the Earth. The Earth also rotates in 24 hours, and thus a satellite in that orbit can stay above the same place on the surface of the Earth at all times. This is called a geosynchronous orbit, and it is perfect for a communication satellite. But how do we get the satellite there? Well, to change the orbit, we need to change our velocity. So we can use rocket motors to do that. And so here's the simplest way to change from one circular orbit to another. Step 1, at some point in our smaller orbit, we fire the rocket motor to speed up. And so this will put us into a new elliptical orbit. We choose this orbit so that its perigee is where we start, but its apogee is at the distance we want to reach. So this elliptical orbit between the initial and final orbits is called our transfer orbit. Here's step 2. Now we do nothing. We simply coast halfway around the transfer orbit without firing our rocket motors. Of course, as we move along that orbit, as we climb further and further from the Earth, our speed will decrease. And finally, step 3. Let's suppose we reach the apogee point. We're moving too slowly to follow a circular orbit with this radius. So we have to fire our rocket motor again, a second time, to speed up again. And when we reach circular orbit speed, we turn off the rocket motor and continue to orbit freely in the larger circular orbit. So, to sum up, we need to use our rocket motor twice. Each time we increase the orbital energy of our spaceship. The first time we shift from the initial orbit to the transfer orbit. The second time we shift from the transfer orbit to the final circular orbit. This technique is called a Hohmann transfer orbit. It's named after Walter Hohmann, a German rocket engineer of the 1920s, and it's a standard maneuver in spacecraft navigation. The Hohmann transfer is efficient and has the advantage of being pretty easy to understand. Now, for more realistic orbit changes, shifting between elliptical orbits that might lie in different planes in space, for example, things can get quite a bit more complicated. All right, here's another basic orbital maneuver. Suppose our spaceship is approaching a planet, Mars, say, from a great distance. The problem is that the spaceship will not just fall into orbit around the planet. The spaceship is moving too fast. The orbit is a hyperbola. The total energy has a positive kinetic energy plus potential energy, positive total energy. So, to enter a closed orbit around Mars, we'll have to reduce our energy. So when we are near the planet, we fire our rocket motors straight ahead to slow ourselves down. And once we slow down below the escape speed, our spaceship will then follow an elliptical or circular orbit around Mars. For every kind of orbit that gravity allows, circular, elliptical, parabolic, or hyperbolic, Some form of Kepler's second law, the law of equal areas, holds true. If we're orbiting the Earth, a line from the Earth's center to the spaceship does sweep out equal areas in equal times. If we're moving on a parabolic orbit around the Earth, the same thing is true. And when the spaceship is close, it moves faster than when it is far away. Why? It turns out that Kepler's second law is really a familiar law of mechanics in disguise. Really, it's just the conservation of angular momentum. Remember, the angular momentum for something moving in a circle is L equal to m times v times r, the product of mass times speed times distance from the center. If something follows a free orbit, L, the angular momentum, stays constant. So if the radial distance r gets smaller, the speed v must get larger. And the product of those two, r times v, determines the rate that area is swept out. So conservation of angular momentum means the line sweeps out equal areas in equal times. Which brings us to Kepler's third law, the harmonic law. Newton perfected it by showing its connection to gravity. For a satellite orbiting a body of mass m, following an orbit of radius or semi-major axis a, with orbital period p, then a cubed equals g over 4 pi squared times m times p squared. Now, we've seen how this law can be used to determine the mass of a distant object in space. For instance, by studying the orbital motions of the moons of Jupiter, we can calculate Jupiter's mass, which turns out to be more than 300 times the mass of the Earth, and about 1,000th of the mass of the Sun. But here's a more spectacular example. The center of our own galaxy, the Milky Way, is actually hidden from our sight by clouds of dust. But infrared and radio telescopes can penetrate those clouds and see stars at the very center of our galaxy. And what do we find? We find that those stars are all moving very rapidly, as if orbiting something extremely massive. We do not see the massive object directly, but we can use the harmonic law to find out how massive it is. And what do we find? At the center of our galaxy is a very compact, unseen body about 3 million times more massive than our Sun. We're pretty certain that it is, in fact, a black hole. Black holes are truly fascinating objects, and we will discuss them at length in Lecture 20. The one at the center of our galaxy is a whopper, but by no means the most massive one that we know about. And how do we know how massive they are? Because the stars and other matter near the black hole, in orbit around the black hole, tell us the mass of the thing they are orbiting. But before we venture too far afield to astrophysics and beyond, we want to consider another aspect of Newton's gravitational physics. This one concerns a phenomenon that is familiar here on Earth. I'm talking about the tides. The story of the tides is about more than the rise and fall of the ocean. It is also about the eon-long process by which the Earth's rotation slows down and the moon's orbit gradually widens. The tides tell us something about Saturn's rings and the giant volcanoes on one of the moons of Jupiter. So, gravity and the tides. Next time. I'll see you then.